So welcome everybody back to this double session of our Gamma seminar. In the second part, we have the pleasure to get Michalina Borczyńska from the Department of Mathematical Physics at the University of Warsaw, who is going to talk about symplectic orbifolds and applications. Thank you, Michalina, for accepting our invitation. The floor is yours. Please go ahead. Thank you.
Okay, so thank you very much for introducing me and my presentation. So today I will be giving I will give an introduction to the symplectic orbifolds and say a bit about their applications. So first, I will start with providing some motivation, and one motivation for studying symplectic orbifolds can be the symplectic reduction. And in the symplectic reduction, one considers a symplectic manifold together with a symplectic Lie group action on this manifold. And also one considers a particular submanifold of this manifold M, which is strictly speaking the level set of the momentum map. And then we also consider a subgroup of this Lie group G that is leaving this submanifold as invariant. And then the goal of the symplectic reduction is to construct a symplectic structure of the obtained quotient space given by the action of this subgroup GS on the submanifold S, which is also compatible with our previous symplectic form omega on M. However, this quotient space need not to be a smooth manifold, and it may have some singularities or can have some more complicated structure. And then, if it is not smooth manifold, we need some more general differential structure to describe this quotient space. And one of the more general differential structure is the orbifold structure. And the spaces, the topological spaces carrying such a structure are called orbifolds, and they are particularly useful when considering such quotients of manifolds by some Lie group. So that was the motivation. And the plan of my presentation will be first introducing the orbifold structure. Then I will say what are the local groups and what is their role in the theory of orbifolds. Then I will define the notion of quotient orbifolds, which are particularly important in the context of symplectic reduction. And at the end, I will introduce a symplectic structure on orbifolds and give an example of symplectic reduction where those symplectic orbifolds arises, and that will be a symplectic reduction of the so-called Hamiltonian S1 manifolds. So to begin, let us define what we mean by a single orbifold chart for some topological space. So suppose that we have some topological space X and some natural number n, and then by n-dimensional orbifold chart for some open subset U of this topological manifold, we mean a triple that consists of a connected open subset U tilde of the n-dimensional Euclidean space, also a finite group G that acts smoothly and effectively on this subset. So the only element that acts as the identity is just the identity group element. And also we have a continuous map from this U tilde subset to the U subset of the topological space. That is invariant under this finite group action and also induces a homomorphism from the resulting quotient space and this open U subset of the topological space. Yeah, so we want to have this map psi to be continuous. Also, we want it to be constant on the elements that that are from the same equivalence class from such a quotient space. And if we denote as pi the canonical projection, we want this relation which uniquely defines the psi tilde function from this quotient to the topological space X. We want this psi tilde function to be also a homomorphism onto this open subset U. Okay, so that was the definition of a single orbifold chart. And now we want to know what does it mean for orbifold charts to be compatible. And for that, we need a notion of embedding between two orbifold charts. So suppose that, again, we have some topological manifold, and suppose that we have two orbifold charts for this topological manifold. And suppose that this first U tilde open subset admits some embedding, smooth embedding lambda into this second U tilde open subset. And if additionally this diagram on this picture is commutative, then we will say that this first orbifold chart, we will say that this lambda is also an embedding between this first orbifold chart and the second orbifold chart. And when we have defined embeddings between orbifold charts, we now are able to define the whole orbifold atlas. So again, if we have, if we have some topological space X, then an n-dimensional orbifold atlas will be a collection of such orbifold charts that associated with those orbifold charts open subset of the topological space will cover the whole space. And also, if we choose any two charts from this collection, for example, with indices I and j, and we take any point from the intersection of the corresponding ui and uj subset of the space X, then we will find also another orbifold chart from this collection, let's say with the index k, such that this point X we have chosen is in the UK subset of the topological space X, and also this UK is a subset of the intersection of the UI and UJ open subset. And also, moreover, we want this third orbifold chart to have embedding into previous two orbifold charts. So we see that this compatibility condition for orbifold charts to be an atlas is quite different than for the smooth manifold, because when we want to have charts of smooth manifold to be compatible, we need just those two charts. And here, to say that two charts are compatible, we need the third chart from this atlas to ensure that those previous two are compatible. Okay, so sometimes we have an orbifold with an atlas, but this atlas is not the best one, and we can equivalently well use another atlas which is in some way equivalent with the previous one. So let us define what does it mean to two atlases be equivalent. So let's take an orbifold atlas A, and we will say that this atlas refines another orbifold atlas B if every chart in this atlas A will admit an embedding into some chart of this atlas B. And then we say that two orbifold atlases will be equivalent if there exists an orbifold atlas that will refine both of the atlases A and B. Now, similar as for the smooth manifold case, we can consider a maximal atlas. And the maximal orbifold atlas will be such atlas that any other atlas which is equivalent with it will be also contained in it. And similarly also as for the smooth manifold case, every orbifold atlas is contained in a unique maximal one. And using this notion of maximal atlas, we can redefine the notion of equivalence of two orbifold atlases and say that two orbifold atlases will be equivalent if they are contained in the same maximal atlas. Okay, and now we are ready to define the notion of the orbifold. So an n-dimensional orbifold will be a paracompact Hausdorff topological space, which will be also equipped with an orbifold structure that is equivalence class of orbifold atlases, n-dimensional orbifold atlases for this topological space. And we will denote the orbifold by the calligraphic old and the corresponding topological space as the normal O. Okay, so now I will provide some examples of orbifolds. And the first example will be just a smooth manifold. So suppose we are given an n-dimensional orbifold, and if for this orbifold we have some atlas that consists only of the charts with the trivial groups, or more generally with the groups that act freely, then this orbifold will be locally homomorphic to the n-dimensional Euclidean space, and therefore it will be a manifold. And furthermore, one can show that this atlas B will then define a smooth atlas for this topological space of this orbifold, and in a result, this orbifold will become just a smooth manifold. I think the simplest example of an orbifold whose corresponding topological space is not a topological manifold is the half line together with the orbifold structure. So in order to define this orbifold structure, we consider the cyclic group the cyclic group Z2, and also its action on the real line given by reflections along the 0 point. So if we want to consider the corresponding quotient space, we have to relate all the points with the same absolute value. And to have the homomorphism between this quotient space and the half line, we introduce the continuous function from this real line to the half line, given by just taking the absolute value, and this continuous function will define this homomorphism between such a quotient space and the half line. So in a result, the half line together with equivalence class of atlas consisting of such a single orbifold chart will be a one-dimensional orbifold. Another simple example of the orbifold is a cone. So now consider the action of a cyclic group of order n on the plane, and its action given by rotations by integer multiples of 2 pi over n. So if we want to have the corresponding quotient space, we have to relate all the points that differ by the angle 2 pi over n, and what we obtain will be the quotient space that will be a cone. So we see that this orbit space, which will be a cone, will define an orbifold consisting of a single global orbifold chart that will define the whole atlas. An example of the orbifold structure that cannot be described by a single orbifold chart will be the structure of football on a sphere. So in order to equip this sphere with a football orbifold structure, we consider again planes and cyclic group Zn acting on this plane by rotation of integer multiples of acting by rotation of angle that is integer multiple by 2 pi over n, and also another plane with another cyclic group acting in a similar way. We obtain here as quotient spaces to cones, in general with different cone angles. And then we consider a continuous function from this plane onto the such a part of the sphere that is almost the whole the sphere, but does not contain the South Pole. And also we require this this continuous function to be invariant under those rotations, and to induce a homomorphism between such a part of the sphere and such a resulting cone. And analogously, we want to introduce a continuous function from such a plane into such a part of the sphere that that is almost all the sphere, but do not contain the North Pole. And we want this we want this continuous function to be invariant under such rotations on the plane, and we wanted to define a homomorphism between this part of the sphere and such a cone. And what we obtain is the structure of the football orbifold structure, which is on the picture. Okay, so we see that in all these examples, some points were a bit different from the other. So in this case, those North Pole and the South Pole are a bit different, and we may call it singular points. Also, for the cone, the tip is different from the other points, and we may call it a singular point. And similarly, for the half-line, the 0 point is somehow singular. And now I will want to say what does it mean for the points to be singular, and how can we say whether the point is singular or not. And for this purpose, I will define the notion of a local group. So consider once again an orbifold and an arbitrary point of this orbifold X. And now if we choose any chart of this orbifold such that this X lies in the image of the function psi from this chart, and suppose that this point X is in the image of the image of the points y1 and y2 from the U tilde open subset from this chart under the function psi. Then, because this function psi has the same value only for the points that are in the same equivalent class, we are sure that those y1 and y2 have to be connected by a G group element. And from that, we obtain that the isotropy subgroups for this y1 and y2 points have to be conjugate. Moreover, if we consider another orbifold chart from this orbifold, such that this point that we have chosen X is the image of y prime point from this U tilde prime subset of some Euclidean space, and it is in the image under the psi prime map, then one can show that the corresponding isotropy subgroups for the point y1 and y prime will be isomorphic. And that result is not so straightforward as the previous one, and to prove it, one has to use some properties of orbifold charts and embeddings that result from the definition. Okay, so now, because of those facts that I said, we can define the notion of a local group. So if we have some orbifold and also arbitrary point for this orbifold, if we take arbitrary chart from this orbifold atlas, such that this point X lies in the image of the continuous map psi from this chart, and it is the image of some point Y, then we say that the local group at this point will be the isomorphism class of the isotropy subgroup for this point y. And this notion is well defined because of the previous discussion. And now let us consider the subset of points with the local group, with some local group gamma. And if this local group gamma is identity, then the set of all the points with the local group, which is identity, will be called the set of regular points. And that is because...
The group identity, you mean the trivial group, yeah?
Yeah, trivial group. Yeah.
Okay, thank you.
Yeah. Yeah, I mean the trivial group. So the set of all the points with the local group, which is the trivial group, will be called regular points. And if all the points for the orbifold, when all the points will be regular points, then this orbifold will become a smooth manifold. And now the set of all the points from the orbifold, apart from those regular points, are called singular points. And one can show that the subset of those singular points of the orbifold is closed and has empty interior. So there is not too much those singular points. Okay, so now we have a following proposition concerning the local groups. So again, suppose that we have some orbifold, and then for any point x for this orbifold, we will have a neighborhood of this point with the associated orbifold chart of this orbifold, such that the group in this chart will be exactly the local group for this point. So, for example, suppose that the point that we have chosen is a regular point. So if it is a regular point, then the local group for this point is just the trivial group. And then because of that, we obtain that we have a neighborhood of that regular point that is locally homomorphic with some open subset of the Euclidean space. That result enables us to prove the following important proposition, that every n-dimensional orbifold will admit an orbifold atlas such that the finite groups from that atlas will act as a subgroup of the orthogonal group. And that result will appear also when considering symplectic orbifolds. Okay, so now I will introduce the notion of quotient orbifolds. So we know that if we have a Lie group action on a manifold, and this Lie group action is proper and free, then for sure the obtained quotient space will be a smooth manifold. And if we assume that we have some weaker conditions, that this Lie group action is proper, effective, but not necessarily free, but almost free, that is, all the isotropy subgroups for this action are finite, then for sure the obtained quotient space will carry some orbifold structure. And the orbifold obtained within this proposition will be called a quotient orbifold and will be denoted as follows. And we will call this orbifold good orbifold when the acting group G is discrete, very good when this group is finite, and in other cases, this orbifold is called bad orbifold. And it turns out that the converse result is also true. That is, every n-dimensional orbifold will be a quotient orbifold for a smooth, effective, and almost free orthogonal group action on a smooth manifold. So that proposition said that every n-dimensional orbifold will be, in fact, a quotient orbifold. Okay, so now I will introduce a symplectic structure on an orbifold, but in order to introduce a symplectic structure on an orbifold, I will have to first say what does it mean to have a differential k-form on an orbifold. And I will define it in a local way. So if we have some orbifold, then a differential k-form on this orbifold will be a family of differential k-forms associated with some maximal atlas of this orbifold, such that each of these differential k-forms on locally defined differential k-forms will be invariant under appropriate group action, and also will be compatible with each other. And this compatible condition will be given by using the notion of embedding between two orbifold charts. And now one can check that to have a differential k-form on an orbifold, we do not have necessarily consider the maximal atlas, but it is sufficient to take an arbitrary atlas, and for each chart for this atlas determine a local symplectic form that satisfy the above conditions, and the symplectic forms, local symplectic forms for the whole maximal atlas are just induced for those previous ones defined in this arbitrary atlas. So now a symplectic form on an orbifold will be just a two-form on an orbifold whose associated local forms with some atlas will be symplectic forms on each open subset of the chart, and a symplectic orbifold will be a pair of the orbifold and define on it symplectic form. For smooth manifolds, for smooth symplectic manifolds, we have Darboux theorem, which says that this symplectic form can be locally written in its canonical form, and we have a similar theorem for symplectic orbifolds. So consider some symplectic orbifolds and some of its atlas A, and then for sure this orbifold must be even dimensional, because we have defined local symplectic forms on each for each chart. So each open subset U tilde must be two-dimensional. So also the whole orbifold has to be even dimensional. And also one can verify that such a symplectic orbifold will admit an atlas such that each group from that atlas will not only act via a subgroup of orthogonal group, and that is result that we obtained for orbifolds. But also it exists such an atlas that also fulfills additional condition that each locally defined symplectic form determined by this omega will be in its canonical form when written in Cartesian coordinates on each U tilde open subset. So, because in such an atlas, each finite group acts via a subgroup of orthogonal group, and also because those local symplectic form must be invariant under appropriate finite group actions. Those group will also act via a subgroup of the symplectic group. So in a result, each of the finite group will act via a subgroup of a unitary group. So to sum up, what we obtain is the Darboux theorem for symplectic orbifolds, and it says that every symplectic to n-dimensional orbifold will admit the so-called Darboux orbifold atlas. That is an atlas where each finite group will act via a subgroup of a unitary group, and each local symplectic form determined by this symplectic form omega will be in its canonical form when written in standard Cartesian coordinates on those open subset U tildes. Okay, so I will give now a simple example of symplectic orbifold, and the simplest example is the symplectic cone. So we again consider an orbifold given by quotient R2 by cyclic Zn group, where this cyclic group is acting by rotation on the plane, and we define a symplectic form on this plane, which is the canonical symplectic form, and then it will be invariant under rotations. So it will define a symplectic form on our cone orbifold. Because we have only a single orbifold chart, so we do not have to check any compatibility conditions. Okay, so our motivation for introducing symplectic orbifolds was the symplectic reduction. So now I will say about a specific case of symplectic reduction that gives rise to symplectic orbifolds. And
sorry, Michalina, just one question. Have you tried to describe a symplectic structure, for example, for an M football?
No, but I will do it for sure.
I mean, you notice that you have two cones, yeah?
Can you repeat?
That in the M and football, you have two cones, yeah?
Yeah.
Good.
Yeah,
so one is with a symplectic, the other one with a symplectic, and then in the middle you have to glue them together.
Yeah.
So you have to check whether it is possible to glue them, but pretty much possible that it is.
Yeah, for sure. I will do it.
Oh, okay. Yeah, do it if you want. Thank you.
Okay. So the manifold we will reduce will be a Hamiltonian S1 manifold, which is a symplectic manifold equipped with a Hamiltonian Lie group action. And it is a group action of a circle group. And we say that a Lie group action is Hamiltonian if its fundamental vector fields are Hamiltonian. And in our case, where we have a Lie group action of a circle group, the space of fundamental vector fields are spanned by such a vector field, which is defined in the following way. So for each point on the manifold, we are acting on this point with the circle group elements, and in a result we obtain a curve, and then we take the tangent vector to this curve, and the obtained tangent vector will be exactly the vector at this point, and that is the value of this vector field at this point. And this Lie group action will be Hamiltonian if we have some smooth function j, such that its differential is the contraction of the symplectic form with this fundamental vector field x. And we say that this smooth function j is a momentum map for this action. And now in a symplectic reduction, one considers the level set of such a momentum map and the quotient space corresponding to the subgroup of the circle group that is preserving this level set and is acting on this level set. And since our fundamental vector field is Hamiltonian, then it follows that this momentum map is constant on the integral curves of this vector field x, and therefore we have that the subgroup of the circle group that is preserving this level set is the whole circle group. And moreover, if this mu from the image of the momentum map is a regular value of the momentum map, then its level set is a smooth manifold, also equipped with the circle group action. And now the aim of symplectic reduction is to endow this quotient space with a symplectic structure that is compatible with our symplectic structure omega on M. And now we have a following proposition that if we have a Hamiltonian S1 manifold with a momentum map J, and we have some point in the image of this momentum map, and it is a regular value of this momentum map, then the quotient space, which is the level set of the momentum map, by the circle group action, will possess an orbifold structure and give rise to a quotient orbifold that will admit a symplectic form induced by this symplectic form omega on manifold M. So we do not need any additional assumption to know that such a quotient space will have a structure of a symplectic orbifold. And now I will give an example of some Hamiltonian S1 manifold and also the corresponding reduced symplectic manifold. So we consider n+1 copies of the complex plane together with the canonical symplectic form on it, and also the circle Lie group action on those copies of complex plane given by rotation of each complex number, and the angle is multiplied by the appropriate weight, and those weights are supposed to be to have the greatest common divisor equal 1, and that assumption that it is equal 1 will ensure that this Lie group action will be effective. And now we can find what is the space of fundamental vector fields for this Lie group action, and we can also check that this vector field is Hamiltonian with the Hamiltonian function J, which is given here. And therefore, this symplectic manifold will, together with such defined circle Lie group action, will be a Hamiltonian S1 manifold with a momentum map J given here. And we can now use the previous proposition and say that for any regular value of this momentum map, and in this case regular values are all negative real numbers, the orbit space corresponding to the action of circle group on such a level set can be equipped with an orbifold structure and become a symplectic quotient orbifold with a symplectic form induced by the symplectic form omega on this these copies of complex plane. And this quotient space is actually homomorphic to the so-called weighted complex projective space. And to define this space, we introduce the weighted Hopf action, and this is the action of the group of complex numbers without zero, given by the multiplication of each complex number by this complex number lambda with the appropriate power given by those weights a's. And then the corresponding quotient space will be defined as the weighted complex projective space. And well, all those a's will be equal 1, then we obtain the standard complex projective space. And that was the example for the Hamiltonian S1 manifold and the corresponding reduced symplectic orbifold. So that's all from me. If you are interested, you have some references where you can read some more about orbifolds and symplectic orbifolds. And thank you for the attention.
Thank you, Michalina, for your talk. I am afraid Javi had to leave
Okay.
5 to 10 minutes ago. Oh yeah, he said it in the chat. Well, anyhow, are there any questions or comments?
Well, I will have a question about
Yes,
this
please, Adam, go ahead.
When you talked about these regular points and their characterization via stabilizer subgroups, namely, in general, we may consider, for example, the sheaf of differential forms on a topological space, and on smooth manifolds, we know that these sheaves are all locally free of rank n. Do you know how this correspondence looks between the characterization of singular sets via this via this stabilizer subgroups and the rank of this sheaf of differential forms at certain points?
I'm not sure I know such a correspondence, but I will check it out for sure.
Okay, but maybe it's in any of these references?
Is this any of these references? I didn't see that, but I didn't see that in those references. But maybe there are. But you know, some of those references has a lot of pages, so I'm not sure. But
Okay, thank you.
you can try to find it.
I will look. Thank you.
Oh, okay. Yeah, you can try to find it here.
So are there any other questions or comments? No? Okay, then thank you again, Michalina, for your talk. And see you all next week. Thanks for attending. Next week, we will have the second part of Ian Anderson's course about superposition formulas for differential systems. So see you all next week. Bye.